Let's look at this function of x here. So we just have this graph for values of x between a and b. We see that there is no y value greater than at x equals a, so f of a is actually a global maximum. Well, we say the function f of x has a global maximum at x equals a. It's the largest value of the function between x equals a and x equals b. F of b is the smallest value of the function, and we call it a global minimum. However, we have a local maximum at x1. So in the locality of the value x1, the function has a maximum. Similarly, we have a local minimum at x0. That means in the neighborhood or locality of x0, the point x0, we have a minimum value for the function. A stationary point on a curve is one at which the derivative has a zero value. So here's a section of a curve. We see that the tangent to the curve at x0 is horizontal. If it's horizontal, its slope is zero. Now, since the derivative is the slope of the tangent, if the tangent has a slope of zero, then the derivative of the function at x0 is zero. So if our function is f, the derivative of the function df dx at x0 is zero. So here's one example of a stationary point, and here's another example of a stationary point. Local maxima and minima are examples of stationary points. The tangents to the curve, this curve at x0 and x1, are horizontal. So the derivative of this function at both x0 and x1 is zero. Now we have to be careful because a stationary point is not necessarily a maximum or a minimum. Take this function here. Look at the tangent to this function at the point x0. We see that the tangent is a horizontal line, so the derivative of this function at x0 is zero. But as we can see, this point is not a local maximum or a local minimum. So it is a stationary point. Let's look at this quadratic function here. If we graph this out, we will get this parabola. We are interested in a stationary point of this curve. That is a point of the curve for which the derivative is zero. So we have to get the derivative of this curve. So if we call this function f of x, its derivative is df dx. So we could expand this out and then differentiate, or we could use the chain rule on this. Differentiate around the brackets to get 2 into x minus 2 to the power of 1 times the derivative of what's inside the bracket. Well, that's just 1. This is multiplied by 1. Set this equal to 0 and solve. So at x equals 2, the derivative is 0. So at x equals 2, we have a stationary point. Now actually, quadratic functions have either a maximum or a minimum. Well, they have a local max or a local min. It's actually a global max or global min. So there's only one solution to this equation. So we must be looking at either a local max or a local min. And actually, it's a local min for this particular function. We could also see that the minimum value of this function must be at 2, because if we plug 2 in here, we get 0 squared plus 2. And that's the smallest value that this expression can have. So 0 squared plus 2 equals 2 is the smallest value we can have, because if we plug in any other value of x, this thing inside the brackets is not 0. And we will be adding a positive quantity onto 2. So we'll be getting a value greater than 2 for values of x other than 2. So when the quadratic is in this form, then the local min or max occurs at, well, the local min actually occurs at x equals whatever this value is, which is 2. And y is then 0 squared plus 2, which is 2. So y is also 2. Next we have a cubic function. So to get a stationary points, we want to set the derivative of the function equal to 0. So if we differentiate this function, we get a quadratic. And set the quadratic equal to 0 and solve. This quadratic has factors. So since we have 0 on the right hand side and we have a product here, that can only happen if one of these factors is 0. So we set each factor equal to 0 and we solve. So at x equals minus 1 and x equals 2, we have stationary points of the function. We can get a rough sketch of the cubic by getting the coordinates of the stationary points. So if x is minus 1, f of minus 1, we plug minus 1 back into the equation of the curve, will give us 13.5. So there's a point on the curve. And if x is 2, if we plug 2 in, 2 in here, we get f of 2 equals 0. So we have another stationary point at 2, 0. So since cubic equations have 2 turning points at most, we can draw a rough sketch. So this one here must be a local max, and this one must be a local min. Let's look at the graph of y equals cos 2x for x in the interval 0.1 to 3 pi over 4. Here's a sketch. Now, we could get a stationary point of this curve by differentiating it and setting it equal to 0 and solving, and we will find that there's a stationary point at x equals pi over 2, but no other stationary point within this interval here from 0.1 to 3 pi over 4. So we could plot the stationary point. Then we could get the value of the function at 0.1 and get the value of the function at 3 pi over 4. Well, it's 0 at 3 pi over 4. And we could then note the local minimum, and we would see that it's also a global minimum. The global maximum occurs at 0.1. Now, here we have a piece of a curve, and you can see that it has a local maximum at x0. Notice that for values of x to the left of x0, the tangents have positive slope. The lines are sloping this way. So the function is increasing for values of x to the left of x0. Well, close to x0, not too far away, of course. But as x approaches x0, we can see that the function is increasing. So the derivative is positive. The slopes of the tangents are positive. However, to the right, we can see that the tangents are sloping the other way. So the slopes of the tangents, df dx, is negative. So you can see that the slopes go from being positive down to 0. So the slopes are decreasing from positive values down to 0, and then the slopes become negative. So we can see that df dx is a decreasing function of x. So df dx looks like this. df dx is positive for values of x near to x0 but less than x0, and df dx is negative for values of x slightly greater than x0. Now let's consider the slope of a tangent to this curve at the point x0. Well, we know to get the slope of a tangent to a curve, we differentiate the curve. So we have to actually differentiate this. Differentiate df dx with respect to x. That's the slope of our tangent. Okay, we evaluate that derivative at x0. Well, shorthand for this thing here is d2f dx2. And we know that the slope of a line is equal to tan of the angle that that line makes with the positive x-axis. We measure anti-clockwise from the positive x-axis. In this picture, alpha is an obtuse angle. If alpha is an angle between 90 and 180 degrees, then the tan of alpha is negative. So the slope of this line is negative, sloping like this. We're familiar with lines of negative slope. So that's the case for when alpha is an obtuse angle. Now it's possible for alpha to be 180 degrees, just as long as df dx is positive for values of x less than x0, which it is, the curve is above the x-axis, and negative for values of x greater than x0. Well, not too far, just in the neighbourhood of x0, of course. So that can happen when alpha is 180 degrees, when the tangent to the curve at x0 is horizontal. So the slope of the tangent is 0, or the derivative of this function with respect to x at x0 is 0. So if you think about it, these are the only two possibilities for when we have a local max of our original function at x0. So we want a local max of our function at x0. So we can only have one of these two possibilities. Alpha can't be less than 90 degrees, of course. If alpha was less than 90 degrees, then our curve would look something like this. Actually, it would look like this, violating what we're interested in. We want the derivative to be positive for values of x less than x0. And that won't happen for alpha less than 90 degrees. Because then the curve would have to continue on and loop back on itself, and we can't have, then it's not a function even. Of course, if alpha is less than 90 degrees, we could have the curve going like this, but that's no good either, because then we don't have a function either. It's negative for some values of x less than x0 and positive for the same values. So we don't want that, of course. So we can only have either this situation or this situation. So for a stationary point that's a maximum, the second derivative is either negative or 0. So d2f dx2 is less than or equal to 0. Now let's look at a graph of the local minimum. We can see that the derivatives are negative for values of x less than x0. So the derivative df dx is less than 0. And for values of x greater than x0, the derivatives are positive. The slopes of the tangents are positive. Lines are sloping this way. So here's a graph of the derivatives against x. So for values of x less than x0, we want the graph of df dx to be below the x-axis. We want it to be negative. And we want it to be positive for values of x greater than x0. So in this picture here, we have the angle beta. That's the angle, the tangent to the graph of df dx makes at x0 and the x-axis. Of course, beta could be 0, like in this picture here. So the slope of the tangent to this graph at x0 is the derivative of the function, that's the derivative of df dx with respect to x at x0, and that's d2f dx2. And that must equal tan beta, so beta will be some acute angle. So beta is the angle between the positive x-axis and the tangent to this curve at x0. And since beta is an acute angle, an angle between 0 and 90 degrees, the tan of it is positive. In this situation here, the tangent is horizontal, so the angle is 0. The tan of 0 is 0. So for the local minimum of a function, the second derivative is greater than or equal to 0. Now let's consider the third possibility. Here we have a stationary point of this function at x0. We can see the tangent is horizontal, so the first derivative is 0 at x0. This is not a local max or a local min. For values of x less than x0, the derivative is positive. The tangents have positive slope. For values of x greater than x0, the tangents also have positive slope. So this is a graph of df dx. It's positive for values of x in the neighborhood of x0. Now, the slope of the tangent to this graph at x0 is 0, which is a horizontal line. So that means that the derivative of this function df dx, or d2f dx2, at x0 is 0. And that's also true if our function looks like this. In this picture, for values of x less than x0, the derivative is negative. df dx is negative. The tangents slope down the way. And similarly for values of x greater than x0. So the graph of df dx against x looks like this. It's negative for values of x in the locality of x0. And as you can see, the slope of the tangent to this curve at x0 is 0. So the derivative of this at x0 is also 0, just like the case for this one. So the second derivative of f with respect to x at x0 is 0 for this type of stationary point. This type of stationary point is called a point of inflection. Now in general, if the second derivative of a function at x0 is 0, we can make no conclusion about the nature of the stationary point. Now here we have an example of a point of inflection, but we can't always conclude that if the second derivative is 0, then we have a point of inflection. That's because we saw up here that for a local minimum we can have a situation where the second derivative is 0, namely when the graph of the second derivative looks like this. Or we could have a local maximum where the graph of the first derivative looks like this. We see that the second derivative is 0. So we could have a local max, a local min, or a point of inflection. We cannot tell. So when the second derivative is 0, our test is inconclusive. However, if the second derivative is strictly greater than 0, then we know we definitely have a local min. And if the second derivative is less than 0, we definitely have a local max.